Hello everyone. This tutorial is a series of video about integrated simulation, including reservoir simulation, well simulation, and production network simulation. For reservoir simulation, we will use software MBAL, and then for the well simulation, we will use Prosper, and then we will integrate the results from MBAL and Prosper to network simulation using GAP. All right, and in this video, we will focus only on the reservoir part using MBAL software. Okay, so we are now inside the MBAL. As you can see, we have file, tool, units, and help. All right, you can open units first, and you can select the preferred unit that you will use in your calculation in your day-to-day work. Okay. All right. You can arrange everything now before the job, before the simulation, or you can change the units later on. Okay. So I just want to show you the units. Okay. I will not change anything now. So I click OK. Now we go to tool and you can see several features, several tools, and we want to use material balance. Okay, again, you can check the units if you want. If not, click OK. All right, so our case today is about gas reservoir. All right, it will produce gas, and the gas will be produced with 4 wells. All right, later on we will simulate the well using Prosper software, and then it will connect to the network, and finally it will end in separator, and we will do that in GAP. Okay, now we will create the reservoir model first. Okay, so we click options. You can follow me, the reservoir fluid gas. Okay, and then tank model single tank, no abnormal pressure, production history by tank, and no compositional model or simulation. Okay, if you have informations like company, field, location, platform, analyst, and any comment, you can put them here. Click OK or click Done. And then we go to PVT, Fluid Properties. Okay. And as you can see, we need to put several fluid properties data. And now I have my data. You can follow me for gas gravity 0.77, separator pressure, all right, at this pressure in PSIG. So you can see the units, the selected units. If you don't want to use these units, you can change the units again here. Okay, so for condensate to gas ratio, this number with condensate gravity of 63 degrees API, water salinity 100,000 ppm, no hydrogen sulfate, but we have carbon dioxide of 0.37 in percent and nitrogen of 4%. Okay, it is better if we match this the laboratory data with correlation. So later on we can use the best correlation that matched our data. Okay, suppose we have and we must have the laboratory data. Click match, and I do the laboratory job in the reservoir temperature 166 degrees Fahrenheit, but I only have 2 points. Unfortunately, I only have 2 points during my laboratory analysis. And the pressure is this one, quite detailed, 0.3. And the second one is at this pressure. And then I measure, I calculate, or I analyze the Z factor 0.906. And for the second pressure, this one. With the gas formation volume factor in cubic feet per standard cubic feet, this number, or quite detailed, right? And this one. Okay. Lastly, for the gas viscosity, all right. Okay, let's say I have 2 points. Okay, and then I want to match it with correlations. Okay, click match. You can see for gas viscosity, we only have Lee et al. Or Carr et al. All right. And the matching is quite easy. You can just click calc and make sure you tick this one, match all. And yeah, there you have the correlation or the matching. First, for Lee et al., we check the standard deviation, the parameter 1 and parameter 2, and you can also check for Carr et al. Okay. Or you can also click this one, match parameters, to see all the numbers. And of course, we can select the best parameter based on what? Based on these parameters. There are at least 2 ways or 3 ways to see which is the best correlation. The first one is by standard deviation. All right. The best selection usually has the lowest or the smallest standard deviation. And between Lee et al. And Carr et al., you can see the standard deviation that is smallest is from Lee et al. You can see e to the power of -8, and here we have -7. So standard deviation in Lee et al. Is smaller than Carr et al. And for parameter 1, we prefer the number that is closest to unity or to 1. And here we have 1.07, but in Carr et al. We have 1.6. So the closest to 1 is actually Lee et al., which is 1.07. And for parameter 2, we prefer the number that is closest to 0. Okay? If parameter 1, we prefer closest to 1, but parameter 2, we prefer closest to 0. Okay, you can see the guidance if you can read or if you read the help. Okay, so the closest one to 0 is actually from Lee et al. Okay, all right. This one is very small, e to the power of -5, but it is bigger. Okay, and then yeah, you can check for Z factor and also gas formation volume factor. Okay. For gas viscosity, you can compare between Lee et al. And Carr et al. But for Z factor and gas formation volume factor, we only have one option. You can see these numbers for Lee et al. But if I change it to Carr et al., no change for Z factor and gas formation volume factor. Okay, so we just want to, or we can only have, or we can do on selection only for gas viscosity. And for gas viscosity, the best one is Lee et al. All right. Okay, so now we can plot, click plot, and then, or I can do the plotting later, click done, click here, or match all. Okay, I click calc again. Okay, so click plot, and you can see we can plot Lee et al. Correlation, Carr et al. Correlation, and also the laboratory data, or here written in match data. Okay, click here, or click the match data first. We have data for gas viscosity, only 2 points. That's why we have line here, only 2 points, the point 1 and point 2. And what about Lee et al. Correlation for Z factor or for gas viscosity? I click this one, click viscosity. So the red line is actually from correlation, generated from correlation, but the black line is actually from data, laboratory data, the real or actual data. And you can see they actually don't match, but it's because we only have 2 points, that side and that side. We don't know what happened in real data, what happened here in this interval. Okay, so we can accept that it's okay. The matching is okay. All right. Especially because at this point, they are actually matched, right? At the same point. Okay, undo zoom, and also at this point. Okay. But we don't know in real life what happened in 3000 psi, 3400 psi, and other pressures. Okay, but Lee et al. Can forecast it, can estimate it, and the estimation is actually this red line. Okay, and we can also plot for Carr et al. Gas viscosity. You can see they are very close. But based on the parameter 1, parameter 2, and standard deviation, we saw that Lee et al. Is better than Carr et al. Okay. All right. So we are done for gas viscosity. What about gas formation volume factor? Okay, this is okay. Yeah, we only have one option for gas formation volume factor and Z factor. Both Lee et al. And Carr et al. Will give the same results. Okay, and let's check the laboratory data. Click it first. Gas formation volume factor, click. They don't match, unfortunately, but this is the best that we can do. Okay, we only have 2 points, but we cannot use this line in our simulation. So yeah, we will use correlation. At the end of the day, we will prefer the correlation because it includes wider range of pressure. In actual data, we only have 2 points, all right? But for correlation, we can cover, yeah, many parameters or many pressures, a lot of pressure, I mean. Okay. And that's what happened also for Z factor. This is from correlation, but in real data, the Z factor is like this. Okay. That's why in your laboratory data, it is better, it is best if you include several points. All right. So you can see the real trend. Minimum 3 points, I think. Not in our case, only 2 points. Okay. But yeah, that's what happened in day-to-day job, right? Sometimes we just need to take it, and from it we need to do whatever best that we can do in our simulation. Okay, so we can close, click done, click done. Yeah, you can see we will use matching. Okay, because we have done the matching. But you can see for gas viscosity, the best correlation is actually Lee et al. That's why I select Lee et al. Okay. And I also want to model water vapor. Okay. To make it more realistic. All right. And then I can click done. Or maybe you can check again. Calculate, match parameters, plot. After I tick the water vapor, what happened? We can check. All right, this is the laboratory data. This is the Lee et al. Yeah, no significant change, no change actually in the matching. Okay, so click done. All right, so this is our PVT data and the selected correlation that will be used in our simulation. So we will use Lee et al. To calculate or to estimate the gas viscosity in 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 the wide range of our pressure. Okay, click done. All right, now we need to go to input. We need to input tank data. Okay, tank data. You can see the tank type is gas reservoir, and I will call it tank 1. The temperature is at 166 with initial reservoir pressure of 5,300 psig, and the porosity is 15% or 0.15 in fraction. And then for the Connaught water saturation is 25% or 0.25. For water compressibility, I will use correlation. And let's say I already know the original gas in place. Okay, based on static calculation or based on other calculations that are reliable, I know that my in place, my original gas in place is 2000 billion standard cubic feet. And I want to start the production from January 1st, 2008. All right. You can check validate. Okay. And then click next. Now we need to input the water influx model. Let's say I already know the model for my aquifer. And I know that, yeah, and I know I have aquifer in this gas reservoir. And let's say I have done the analysis and I know that to best match the aquifer performance, I should select this one. And the system is radial aquifer. And let's say I already know the reservoir thickness is 120 in feet. Reservoir radius, let's say I already know 5,000 feet with outer inner radius ratio 5 and encroachment angle 100 degrees, 180 degrees with aquifer permeability 20 millidarcies. Okay. And then for the rock compressibility, let's say I know the exact number from my core data. I select user specified 3,5 e to the power of -6 per psi, right? The unit for, yeah, this one, rock compressibility. Okay, and then for the rock compaction, no need to input it. Let's keep it as default. And relative permeability data. Here we will use Cori functions to generate the rel-perm, the relative permeability. Hysteresis no, in our case. And water sweep efficiency, let's assume 100%. And for this table, relative permeability to water, the residual saturation, 25%. You can see here, Connaught water saturation, right? And then for the gas relative permeability, the residual saturation 0.1, the endpoint 0.3 for water, and for gas 0.8. Okay, of course, higher than the water. And the exponent 2,5, 1,5. Okay, you can click plot and you can plot removal first, the gas relative permeability, versus gas saturation, and also this one. Okay, the gas relative permeability versus water saturation, and also this one, relative permeability to water versus water saturation. Okay, so far so good. Let's say we haven't produced the reservoir. Okay, so I will not include production history. And because we don't have production history, we will not do history matching. No need for that. So we can click validate, click done. Okay, so you can see we have this tank reservoir, the red color, and the aquifer, the blue color. Again, I click, you can see we don't have production history. We haven't produced the reservoir. Okay, we still don't have any well right now. Click done. That's why we don't need to do history matching. These items will all be inactive. Okay, and now let's check the production prediction. Prediction setup, profile from production schedule. Yeah, we can select. Yeah, actually, we will not do the prediction or the forecasting using MBAL. The job will be done by GAP. Okay, later on, we will connect this model with GAP software. But yeah, we can select this one, prediction profile using well models, options use fractional flow models, right? Prediction start of production, and then user define prediction end will be ended at this date. Yeah, just to make it prepare for any simulation or for any forecasting, I will set up this production calculation setup like this one. Okay. And then for the production and constraints, I have these constraints, for example. So at 2 January 2005, the manifold pressure or the system pressure is 2000 psig. Yeah, the system pressure or the manifold pressure or the separator pressure or wellhead pressure, 2000 psig. Okay, basically they are different. Separator pressure is not manifold pressure. Manifold pressure is not wellhead pressure, but I think MBAL want to simplify that and they will call all the surface pressure as man pressure or manifold pressure. Okay, so it's not bottom hole pressure, it's not reservoir pressure, it's surface pressure. Okay, and let's say the constraint for gas rate maximum F 250 mm SCF per day or million standard cubic feet per day. And then at this date, at 2011, I will decrease the pressure, the system pressure, the surface pressure to extend the life of the reservoir. Okay, so far so good. And done. Okay, actually we can do the forecasting using this model, prediction setup, profile from product schedule, no wells. Okay, in this configuration we don't install any well, so the forecasting will only done by the tank reservoir itself. Click done. Okay, and then for the reporting schedule, automatic, and then production constraints. Actually, I need to redo that, or for example using wall model again. Okay, but yeah, if you use Using well model, you need to connect it with well. So you need to prepare the well first. Okay. Yeah, actually, if we don't want to install any well in this model, we should select this one, profile from production schedule, but the production and constraints will change because we don't have well. We cannot consider the surface pressure. All right. That's why the only constraint is only date and the average gas pressure or gas rate. Okay. The average gas rate. We can keep it constant for several time, all right, for some time, and it will decline. You can do that actually. Let's do that. I want to take the date. For example, it will produce at this one, January 1st, 2008, right? 2008. And let's say the gas rate 250 million standard cubic feet per day. Click done. Reporting schedule automatic and check the prediction. All right. You can see from 2008, January 1st, down to the end of prediction, which is January 2015. And you can click plot, check the prediction, the tank pressure. So the reservoir pressure will decrease from 5,300 down to this one, 3,038 here, the last point. And we can also check the gas rate. So from 2008 to 2015, we can maintain the production rate at 250 million standard cubic feet per day. What happens if I increase the production significantly to this one, 2,500 million standard cubic feet per day? Okay, or if it is too much, yeah, let's check just for example, right? For the case of example, you can see the reservoir pressure dropped to zero because the in place is only here, 2000 BSCF. So let's say I only want to produce at, yeah, this number. Let's predict what happened. Plot. Yeah, we can still keep the gas rate, but you can see the reservoir pressure reduces to a very small pressure, only 200, which is doesn't make sense. All right. Yes. So this is what happened if you simulate but without wells. Okay, you will get unrealistic results like this one because in reality the reduction of the pressure is too big. All right. Actually, we cannot produce at manifold or at surface pressure lower than 200, right? 215, if that matters. Okay, so yeah, you can do simulation like this, but it's not realistic. So again, we will go back to production profile using well models. Okay, and we will have production constraints like the earlier, but the well will be constructed using Prosper, and then we will connect the well and the reservoir using GAP. Okay, we can actually connect the well using this software only. All right, this software alone can do that, but we want to connect it with network simulation. So better if we do integrated simulation. Okay, we have completed the reservoir discussion. we have created the reservoir model. So yeah, from here we will go to the next section, which is about well simulation or well modeling using software. And later on in the later section, we will connect the MBAL model, the reservoir model, with well model, the Prosper model, with network model, which is GAP software. All right. So let's continue. And we will continue our learning on simulation. In previous video, we are talking about creating a gas reservoir model using MBAL. By the way, we are still in series of videos about integration between reservoir model using MBAL, well model or well simulation using Prosper, which we are now using, and with production facility or network model or simulation using GAP software. All right. In the previous video, we have constructed a reservoir model using MBAL. We constructed a gas reservoir model. And as I said before, we will produce the gas using 4 wells. Okay, so in this video, we will construct 4 well models to represent 4 wells. And the 4 wells will take the gas from the reservoir, and the gas will be produced through the production facility, whose model will be modeled using GAP software, which we will discuss in the next section. Okay, so now we will concentrate only on the well modeling, well simulation using Prosper software, and we will construct yeah, I think it's a typical well without artificial lift, gas well. So it will be quite easy, quite simple. All right, so let's do this. So as you can see, we are now inside the Prosper. In the software, we have this section to show the picture of the well. Okay, and then this is the starting point. This will be section for PVT. This is for the reservoir or the IPR, inflow performance relationship. And this is about the well itself, the construction, the configuration of our well. And this is the list of analysis that we can do. All right. And we open this first. Okay, you can follow me. For the fluid description, fluid, we will select, okay, open the drop-down menu. Right, wait a minute. Dry gas, I mean dry and wet gas. Okay, method black oil, single stage separator, disable warning for PVT warning, water viscosity we will use default correlation, and for the water vapor, open the drop down menu, we will use calculate condensed water vapor. Okay, so there will be water vapor inside our gas, and we will calculate the condensed water vapor. All right. And flow type, tubing flow, well type producer, method none. Okay, you can input the company, field location, well, and so on and so forth, but we will skip them. And also the comments. Okay, yeah, we can type in well A. We will have well A, B, C, and D. Okay, and for the calculation type, predict, let's say it's an offshore well. Model, rough approximation, the range full system, brine properties default. It is a case hole completion, nose and control, and for the reservoir inflow type, single branch. Okay, we can click done, and we will wait for a while until the Prosper or the system is ready. Okay, wait a minute. All right, yeah, you can see everything is open. Now we go to the next section, PVT section, open this one, PVT input data. Okay, so you can follow me for the gas gravity 0.77, separator pressure at this pressure, and let's say the condensate gas ratio 22.2 and the condensed gravity 67 with water gas ratio of 1, water salinity 100,000. It is similar with the data that we use in the MBAL model. Okay, so you can open again the MBAL video and you can cross-check the data. Okay, so the water salinity 100,000 ppm, H to S0, and then for the mole percent of carbon dioxide 0.37, and for the nitrogen it will be 4%. Gas viscosity we will use Lee et al. And as you can see for the other data, water viscosity we will use correlation, water vapor, calculate condensed water vapor. Okay. Reservoir data, reservoir temperature 166 and the reservoir pressure 5,300. Water vapor data, automatically populated the data 0.27 minimum water gas ratio, and we can open the water vapor plot by clicking this button. Yeah, you can see the plot of saturation WGR versus pressure. Okay. It is very important, right, for gas well, especially water gas ratio, including the water from the condensed water. It is important. So of course we need to model it. Okay. And then click done. Okay. And then for, yeah, we need to do matching here, just like what we did in MBAL software. So open the match data. Here we will do the match data. All right. Just like before, we only have 2 points. The reservoir temperature is 166 and the point is like this, the pressure, Z factor, gas viscosity, gas formation volume factor, and for the second pressure, okay, the Z factor, gas viscosity, and for the gas formation volume factor. Check again the unit, PSIG for the pressure, gas viscosity for the centipoise, centipoise for the gas viscosity, and gas formation volume factor, cubic feet divided by standard cubic foot. All right, so far so good. And now we can click match. Match all. Be careful here. Let's see what will happen. We have 2 points here, the real data, and the red line is actually the correlation results. Let's check it out if we click this button. By the way, we can check also the gas viscosity by clicking this button. You see, they don't match, right? The actual data, the 2 black points, the red line is Lee et al., the blue line is Carr et al. And for the gas formation volume factor, it's quite matched already. But we still haven't done any matching. So let's check it out. Click this button, match all. If I click this button, match all, the Prosper will do the matching. Okay, let's check it out. Okay, so now you can see the Prosper matches our data with the correlations. So for the Z factor, it's very good actually. For the gas viscosity, very good. right? And for the gas formation volume factor, also the matching is very good, even better than what we get in MBAL software, all right? And to select the best correlation, let's check the statistics. First, for the Z factor and gas formation volume factor, we don't have any selection, okay? We can only take it. For Z factor, parameter 1 is quite close with 1, so okay. Parameter 2 is close to 0, so it's okay. Standard deviation, e to the power of -8, which is very small, so it's satisfactory. It's good. Gas formation volume factor 1.077, quite close with 1. Parameter 2 -0.000, very close to 0, so it's good. And for the standard deviation 7.2504, e to the power of -5, which means times 10 to the power of -5, which is very good. Okay. And for the gas viscosity, Lee et al. Has parameter 1 closer to 0. All right, compared to Carr et al. Because Lee et al. Is 1.066, whereas for Carr et al. Is 1.6. And for parameter 2, Lee et al. Is closer to 0 because it is 0.000, whereas Carr et al. It is minus 0.007. Okay, so for parameter 2, Lee et al. Is better than Carr et al. And for the standard deviation, these two equations have the same standard deviation. So in conclusion, Lee et al. Is better than Carr et al. All right, just like what we get in MBAL software. Okay, Lee et al. Is better than Carr et al. So we will select Lee et al. As our correlation. Yeah, you can check the parameters by clicking this button. The same result actually, like what we have here. Done. And also create the plot or plot all, like this one. Exactly what we have in this small section. Okay, we can get, or we can plot the Z vector, gas viscosity, okay, gas formation volume factor, and also gas density. Click done, done, done. You see the sign, PVT is matched, which is good. And we will select gas viscosity correlation Lee et al. Instead of opening this drop-down menu, instead of Carr et al. We select Lee et al, click done, and now we go to the next section, which is IPR, Inflow Performance Relationship. Open this button. To model the IPR, we select Petroleum Experts Correlation. Okay, it's a proprietary correlation or equation or model owned by petroleum experts. Okay, so yeah, we can use it. It's quite good. And for the skin, we will model it using Caracas and Tarik equation. Whereas for the deviation and partial penetration skin, we will use Chincho 2 Martin bronze. Okay. And reservoir data, reservoir pressure is 5,300, automatically populated. Okay. Just we just want to check it. Reservoir temperature is 166. Okay. Water gas ratio is 1. Condensate gas ratio is 22.2. Stock tank barrel per million standard cubic feet. okay, or food. All right, now we need to input data for the reservoir model. So reservoir permeability 25 millidarcies, reservoir thickness 120, in feet, drainage area 420 acres, DH shape factor 31.6, assuming circle reservoir, wellbore radius 0.354, perforation interval 75 feet, time since production started, so it's a transient model. Let's assume 75 days with reservoir porosity 0.5, I mean 0.15, conduct water saturation 0.25. Okay, for the non-Darcy flow factor, D will be calculated. Beta factor method original. Permeability entered is total permeability. Okay, and now we need to input the mechanical and geometrical skin. Okay, reservoir permeability 25, shock density 8, perforation diameter 2 inches, perforation length 4 inches, perforation efficiency assuming 1, damage zone thickness 6 inches, damage zone permeability 8 millidarcies, crack zone thickness 0.5, crack zone permeability 4. So yeah, you can see the model, the Caracas Tarik model is very detailed. Okay, so yeah, we can use it, we can follow it. In this case, we need to provide this thickness, the damage zone permeability, crack zone thickness, crack zone permeability. We need to provide that data into the Prosper model. Shot facing for the perforation. Okay, so the mechanical geometrical skin will consider the perforation configuration. All right, this equation by Caracas Tarik. So for the shot facing of the perforation is, let's assume 120 degrees, wellbore radius 0.354, and vertical permeability 2.5 millidarcies. Okay. And for the deviation and partial penetration skin, deviation assuming 0, penetration 1, 100%. Okay. So all the thickness of the reservoir 120 will be open, will be penetrated. Okay. And then for the vertical permeability, 2.5 millidarcies. Okay, so now click calculate. And by clicking calculate, you get the non-Darcy flow factor and also this AOF, or absolute open flow or maximum flow rate. Okay, so far so good. And we can construct the IPR, plot results, plot the rate in x-axis, and plot the pressure on y-axis. Click done. Let's wait. All right, so this is our IPR. You can check the skin 7.14, the total skin, with perforation skin is 5.27 and damage skin is 1.87. So if you combine the perforation skin and damage skin, you will get total skin of 7.14. And the absolute open flow is 145.989, or yeah, basically the LF 146 million standard cubic feet per day. Okay, this is the main results. Click finish, click done, click done. So we have completed the IPR section, and now we need to construct the mechanical aspect of the well by clicking this section. Input data, deviation survey, downhole equipment, and also let's check the geothermal gradient and also the average heat capacities. Click edit. Okay, so now you can follow me for the deviation survey, the trajectory of our well. Okay. Yeah, actually it's a deviated well, but in the IPR section, we input the deviation is 0. That's okay, because basically what we did in that section, we want to calculate the skin due to deviation. And yeah, let's neglect that. It will not be very big. Okay, so we input 0 just to make the skin factor quite conservative. Okay. And then this one. Okay. Okay. 4140, 5000, 4560, 5400, 4900. All right, this is our trajectory. You can plot. Okay, we have a vertical section here and deviated section here. Okay, click finish and also click done. Now we need to construct the downhole equipment starting from Christmas tree at 0 depth. And then we have tubing down to 1000 feet with tubing ID inside diameter this one. We use default roughness. And then we have subsurface safety valve inside diameter of 3 inches. And then tubing again. Okay. Open the drop-down menu down to 5000 feet with the same ID with this. And lastly, we have casing. From the top of the well down to 5400 with casing inside diameter of 6 inches, and we can use the same roughness. Rate multiplier 1. Okay. And then we click done. Now we need to input the geothermal gradient. Okay. 45 degrees Fahrenheit, 75 degrees Fahrenheit. And at the reservoir depth, let's say 122. I mean at this depth, 5400. Okay. Click done. And we can use the default numbers for average heat capacities. Click done. We can check the summary by clicking this button. All right. In table, we can also draw. You can see this is the configuration of our well. Starting from Christmas tree, tubing, we have safety valve, tubing down to this depth, 5000. And we have casing. Okay. Yeah, the casing in reality should be from the top. Okay. But of course, this diameter is not, yeah, not necessarily starting from the top, because on the top we usually have surface casing, conductor casing, right? This is for the production casing, whose tubing inside diameter, whose inside diameter is 6 inches. All right, click done, done, done. So far so good. So let's wait for a while. All right, so this is the well sketch, the well configuration. It means we are now ready to perform the nodal analysis or the simulation. Okay, click calculation, system, IPR VLP, and let's assume the wellhead pressure, the top node pressure is 2100 with water gas ratio of 6 and condensate gas ratio of 22.2. Later on, the wellhead pressure will be based on the gap, not based on the prosper. Okay, so now in this section, we just want to do the calculation for, yeah, for our interest. And then for the solution at bottom node, right method, yeah, we can use this. For the vertical lift correlation, yeah, we can use petroleum experts too. All right, all good. We can click calculate, show calculating data. Okay, we get the nodal analysis, the IBR, the red line, and also the VLP, the blue line. We can check the plot here, or we can also check the plot by clicking this button, plot, system plot, plot all cases, x-axis, the gas rate, y-axis, the vertical axis, VLP and IPR. Click done. All right, so this is our nodal analysis. Okay, so we have constructed one well. Later on, this well will be connected to the MBAL, to the reservoir in the gap. Okay, so now we need to construct 3 more wells, but basically they are typical. So I will just copy this model and paste it for 3 times. So I have well 1, 2, 3, and 4. And then for the well 2, 3, and 4, I will just change the properties, change the parameters, but basically they will be typical. Okay, so we can get 4 wells, and in the next section we will connect 3 wells. We can connect 4 wells with the gap, which is the production or network software, production network modeling software. Okay, so we can save this model and we can copy it 3 times, and we can have 4 well models, which are typical. Okay, so I'm just going to, okay, so this is the first well, well 1, and I will just start from this file, this well 1, and I will do some modifications and save it as well 2. Okay, so now we will use well 1. Okay, we will keep many data. Okay, we will keep the majority of this configuration, and we can change few parameters and then save the file as well too. Okay, so let me check. Okay, everything will be kept. All right, click done. And then for the PVT, everything will be kept. All right, already matched. Click done. And then for the, yeah, let me check again. Okay, water gas ratio. Yeah, I will. Yeah, we should keep it. We must keep it. Yeah, you see, This is actually well 1 Eng-Man, but I will save it as well 2 Eng-Man. Okay, so I just use the first file, okay, to make my life easier. Click done. And then for the IPR, okay, the same reservoir pressure, temperature, okay, the same reservoir permeability. But let's assume in this second well, the reservoir thickness is only 50 feet. Okay, so the thickness of the reservoir is not uniform, some thicker, some thinner. Okay, so let's say it is thinner in well 2 with, okay, drainage area of 500, the same wellbore radius, perforation interval, let's assume, yeah, 100% of the reservoir thickness will be perforated. So the perforation interval is 50. Time since production started 1, porosity 15%, connate water saturation 25%. Okay. And then for the mechanical geometrical, reservoir permeability the same, density, shot density 8. Perforation diameter in this well, let's assume 2.5 inches. Perforation length 4. Perforation efficiency 1. Damage zone thickness, damage zone permeability 12. Crack zone thickness, yes. Crack zone permeability 8. Shot facing, okay. Wellbore radius, okay. Vertical permeability 2.5, okay. It's good. In the section, the same. Now we can calculate, okay. Or I can leave it blank first, if I can, or not. Okay, already calculated. All right, in this well, the AOF is smaller compared to the first well. The AOF is only 92.5 million standard cubic feet per day. So you can check the results. Click done. This is the IPR. Okay, the skin, perforation skin, damage skin, the absolute open flow. Okay, click finish, finish, finish. Yeah, at this point we can save this file first and call it well2. Okay, I will do that. Okay, so now we are now well2. Actually, I have saved it as well2. Okay, I will do the same. Edit. Let's check the trajectory. Okay, the trajectory, let me check my data, the same. Okay, we can keep the same trajectory. And then for the tubing or the well configuration, yeah, the same. Click done. The temperature should be the same and default heat capacities. Okay, click done. Click done. Now for the nodal analysis, click calculation, system IPR and VLP. Let's say the top node pressure, the wellhead pressure is 430. And yeah, we can calculate. All right. So the top node pressure here is smaller, just to check it, because later on the wellhead pressure will be based on the gap. Okay, by lowering or by having lower top node pressure, of course we can increase the gas rate. That's why we have the intersection between, or the intersection between IPR and VLP at this far right side, and we can produce at rate of 70.7 million standard cubic feet per day, which is very big. Okay, so again, you can check the plot, system plot, plot all cases, done. Yeah, this is our second well, the nodal analysis for second well. Click finish, finish, save. Okay, so we have completed the second well. I will start using this second well, okay? And then I will name it as well 3, and I will do some modifications, okay? I will pause for a while. Okay, so now we are in the third well, okay? I use the file from well 2, okay? Or I can also use the file from well 1 and do some modifications and call it well 3. Okay, let's do some modifications. Okay, let me check this section first. Okay, everything is good. No problem here. Okay, click done. And also the PVT. Okay, let's check the IPR. Let's say the reservoir thickness here is 70 feet with drainage area of 500. Okay, the same. Perforation interval 70 feet. All the thickness of the reservoir is perforated. So 70 feet. Time since production started 1. Reservoir porosity 0.15. Connaught water saturation 0.25. Okay, the non-derisive flow factor will be calculated. Check the mechanical geometrical skin. Shot density 8. Perforation diameter 2.5. Now the perforation length is 6 inches. Damage zone thickness of perforation length, yeah, 6 inches. Damage zone thickness 8 inches with damage zone permeability 12 millidarcies. Crush zone thickness 0.5. Crush zone permeability here is 12. Shot facing 120. The same will radius, vertical permeability 2.5. Okay. And again, we can keep it like this one. Calculate. Okay, now we get higher AOF, higher absolute open flow compared to the previous one. The second well, the well 2, has absolute open flow around 90, if I'm not mistaken. But now the third well has AOF of 139 million standard cubic feet per day. Plot results, click done. Okay. Finish, done, done. Let's check the trajectory, check the downhole equipment, check the geothermal gradient, edit. Okay, I will maintain the trajectory, the same. Done. Check the downhole equipment, exactly the same. Yeah, in reality, they should be different between one well and another well. But yeah, for the sake of example, okay, we will copy or we will have the same, exactly the same well configuration. So no problem there. Okay, done. Check the summary if you want. Drawdown hole. Okay, done, done, done. All right. For the sake of completeness, we can do nodal analysis, system IPR VLP with, for example, the wellhead pressure 700, top node pressure. Let's assume water gas ratio of 1, and we can click calculate, show calculating data. Be careful. The second well has operating gas rate of 70 million standard cubic feet per day with wellhead pressure 400, right? 430 PSIG. Now, what will happen if we have higher top node pressure of 700? Calculate, show calculating data. Okay, we can get higher operating rate of 92. Do you know why? Because now we have, or we assume, smaller water gas ratio of 1. Previously we have 6, which make the flow heavier. Now the water gas ratio is smaller. That's why we will have operating gas rate higher, 92. What will happen if we have the same water gas ratio as the previous case of 6? Calculate, show calculating data. Yeah, the water gas rate, I mean the operating gas rate is actually smaller only, but still higher than the second well. Okay, here we have 91. Why? Yeah, because basically the IPR, the absolute open flow, the reservoir influx for the second or for the third well is better, all right, compared to the second case. Okay, so I think we can go back to water gas ratio of 1, calculate, show calculating data. Okay, done, and save it as well tree. Yes. All right. Lastly, we can file, save as well for. Okay. Okay, so now this file is well for. Save. You can see well for. Yes. All right. And check this one. That should be the same. Done. Same PVT. Okay, same PVT. Well for Eng-Man. Done. The IPR should be the same or should be different. Now the reservoir thickness is 80 feet. Drainage area smaller, only 300 acres. And also the perforation interval 80 feet. All the thickness of the reservoir is perforated. Okay. And for the mechanical geometrical skin, 25, 6, 2.5, perforation length 8, perforation efficiency 1, damage zone thickness 6 inches, damage zone permeability 12 millidarcies, crash zone thickness 0.5, crash zone permeability 6 millidarcies, shot facing 120, well radius 0.354, vertical permeability 2.5. Keep the deviation and partial penetration skin. Yeah, you can check this number. This number will be changed if I click calculate. All right, there. And now the absolute open flow is 162 million standard cubic feet per day. Okay, click plot results, done. This is the IPR. Okay, the IOF, skin, and perforation skin. Finish, done. Let me check again for the mechanical and geometrical skin. This, okay, 8. All right, okay. Okay, so now click done. Now check the well configuration, deviation survey, downhole equipment, geothermal gradient, edit. Again, the trajectory is the same. You can check again the plot, the same trajectory. Finish, done, the same well configuration, and the same geothermal gradient. So very easy, right? Done, done. Okay, lastly, calculation, nodal analysis, system IPR and VLP. Let's check if we have high wellhead pressure of 1000 psig. Click calculate, show calculating data. Yeah, although we have high top node pressure or high wellhead pressure or high back pressure, but we can still operate at high gas rate of 99 because basically we have good influx. The reservoir performance, the IPR is good. So that's why we have the intersection between IPR and VLP quite high, which gave us operating gas rate at 99 million standard cubic feet per day. Okay, you can plot, system plot, plot all cases, done. Okay, so far so good. So we have constructed 4 wells. To make sure, click save. Okay, so in the previous video, we have constructed the reservoir using MBAL software. In this video, we constructed 4 wells, which are typical, but they have different IPRs. Okay, we have constructed 4 wells, and the 4 wells will produce the gas from the reservoir. So we will connect the reservoir with these 4 wells, and then connect the 4 wells with the production facility, production network. And the network, the system will be modeled, will be simulated using GAP software, GAP, GAP, and we will discuss about GAP software in the next section, okay? So now we will continue our learning on simulation. Previously, in the first section, we have created a reservoir model using MBAL software. We created a gas reservoir model. And then in the second video, we have learned about the creation. We constructed 4 wells, 4 typical gas wells that will produce the gas from the reservoir. Okay. And now we will we will construct production facility, production network, and we will model it using GAP software. Okay, and we are now inside the GAP. The software is really an interesting software. It's a production network modeling software, and With this software, with this modeling, we can integrate the reservoir model from MBAL, well model from Prosper, and the network itself using this software. Okay, so first I will introduce you this software. As you can see, we have several tabs: file, options, view. Okay, here we can draw solid line connections and others, edit, flow assurance. If we want to put some constraints in our system, we can do that here. System constraints, generate. We can generate well IPRs, well VLPs, and so on and so forth. Later on, we will learn some of the features here. Model validation, solve network, transient, prediction, results, reports, window, units. Let's check the unit. You can see we select oil field units. Okay. If you want to edit the units, select this one. Okay. The look is actually like what we have in MBAL, right? So for example, if you want to see diameter, so here the unit is in inches. Okay, we like that. Energy in MMBTU, million British thermal unit. Enthalpy BTU per pound, and so on and so forth. Gas rate in million standard cubic feet per day. Okay. Okay. Click OK. So for the units, we like this. Okay. Oil field unit. And to learn more about MBAL, you can open help, contents. Okay. You can open the index. All right. Search. Okay, I will close. New, to create new sheet. Okay. Open. Save the model. New window. Edit equipment controls. This is to run network solver. This is to edit the prediction script. This is to run the prediction. And this is the item that we have. First, we can install separator, join. Okay, we will use join a lot. This is to construct link, okay, or pipe, flow line, trunk line. We can use this icon. This is to model a well. All right. So the model we can put using this one and then connect it with Prosper. I will demonstrate that later. This is for tank or reservoir. This is the flare, pump, compressor, source or sink, inline element, inflow, okay, group, flow sheet, SJP. I don't know what it is. Oh, it's valve. Okay. Right click, delete. User defined inline element. Okay. Heat exchanger. Zoom in, zoom out, unzoom, mask, unmask, disable, enable, delete, move, select, unselect all items, find equipment on system window. All right. Production model, water injection model. Okay, we are now in production model, gas injection model, gas lift injection model, index, undo. Okay, so now first we will construct the big picture of our system. Okay, you can follow me. First, this one, add tank. Click tank. You can see add tank and put the model here. All right. So this is our tank. This is our reservoir. We can call it gas reservoir, for example. Click OK. All right. Gas reservoir. And click that again. Okay. So that we can have select in our cursor. Now I will put 4 wells here at well. 1, I call it well 1. And then 2, I call it well 2. And then 3, I call it well 3. And lastly, 4, I call it well 4. Don't forget to click this item again. Okay. And then I will connect my reservoir with these 4 wells, okay, to symbolize that these 4 wells are drilled into this reservoir, and these wells, okay, these 4 wells will produce gas from this tank, from this gas reservoir, okay. And to link that, I use this one, add link. Click, touch the gas reservoir, okay, hold on, left button, touch the well 1. Done. The connection already constructed. And then the second one, click, hold the left button, put the connection on well 2. Okay. And then for the well 3, all right. And lastly for well 4. Okay, so far so good. Click that again. Okay, I can move the pictures, the icons like this. Okay, and then I will connect the well, these wells, with the main flow line. Okay, or we can also call it header, for example, bigger flow line. Okay, and so that we, in order to be able to connect the well, we need join. Okay, join 1, and then join 2, join 3, join 4. Okay, first connect the well with these joins. Click, touch well 1, connect it with J1. Do that also for well 2, well 3, well 4. Okay, click, and then I will use, okay, I will move them a little bit. Okay, and then another join here. Okay, J5. And then I will connect J1 and J5 and also J2 with J5. And the connection between each join is actually represented by pipeline or flow line. Okay, so that in reality or in our imagination, we can imagine that the well, okay, will be connected to flow line, and then the flow line will be connected somewhere in the network. For example, they connect in manifold, and from the manifold to the station, they will flow inside bigger flow line or bigger pipeline. Okay, so let's construct the flow line from J1 to J5. Okay, so you can see the picture is quite different. Here we only have connection, okay, which is actually, it's not a pipe, it's just an imaginary connection between well and the joint. But here in J1 in J and J5, it's actually a flow line or a pipeline, okay, flow line or pipeline. Okay, so it's not an imaginary connection, it's actual line, pipeline, or flow line. Okay, and also J2 and J5. Okay, so now I have one reservoir, 4 wells, and 2 flow line. Okay, connected in this joint. Okay, and then click that again. I want to put another joint here, J6. And again, I will connect J3 and J6, J4 with J6. I will construct the flow line, the flow line. All right. And actually, we can change the name J5 and J6 with manifold. So I will select and then let me check. Can I double click the J5? Okay. Okay, so let's do that again. Close. Double click on J5. You see the label J5. I can change it to manifold underscore A. Okay, so I call it manifold A, and okay, I will drag them down and double click on J6. All right, I will call it manifold B underscore B. Okay, so far so good. Now I will connect manifold A with manifold B to represent another flow line. Okay, usually this line will be bigger than the flow line from each well. Connect, touch manifold A. Okay, hold the left button, connect it with manifold B. Okay, and also another join there. Okay, I call it separator joint. Okay, there. And I will connect the manifold B with separator join. I will rename it join. Okay. All right. Connect it with flow line or pipeline. Okay. And lastly, from this join, I will connect it with the separator. And it is production separator. I will call it separator. Okay. Okay. Click that again. I will move the separator there. Okay. Click the move again. Now connect the separator join with separator. All right. Beautiful, right? So as you can see, we have constructed the big picture. So as I said before, I have one gas reservoir and I have 4 wells drilled into this well, into this reservoir. So I have 4 gas wells. And then I have flow lines connecting this flow line with the production network. Okay, so we can call it production network, production facility, production pipeline system. All right, I prefer network in this video. So the network, the center of the network will be the separator. Okay, so all the flows will be directed into the separator. The pressure of the system will be based on the separator pressure. Okay, so if you want to do production optimization, production debottlenecking, basically what you change or what you change is the separator pressure. Okay, of course, if the separator pressure is high, then the situation, we can call the situation back pressure, high back pressure. And we don't like actually the high back pressure because it makes the flow more difficult to flow. Okay, more difficult for the fluid to flow against the high back pressure. Okay, so usually we can do optimization by lowering the separator pressure. Okay, or lowering system pressure. If we lower down the separator pressure or the system pressure, at the end of the day, the wellhead pressure will be lowered also, will be reduced. And with lower wellhead pressure, usually we will have higher flow rate. Okay, so that's the concept. Okay, this is the first stage of our simulation. So far, so good. Now we need to connect this reservoir with the MBAL model that we have created. So double click. Okay, let's check it out. Label gas reservoir, name also gas reservoir if you want, model material balance. Okay, it's still inactive, but you can see the MBAL file is missing. So we need to fill this window, this model with MBAL model. So click browse. Okay, and then we will select the MBAL model that we have created. All right. Okay, this one, the file is gas reservoir Eng-Man. And as you can see, it is valid. This gap will read, and from the MBAL model, this software knows that the original gas in place is this number. Okay. And then the type is gas reservoir. Number of tanks 1. Tank ID is tank 01. Start of production in January 1st, 2008. Well connections okay. Constraints none. Injection fluid gas. Schedule none. Yeah, we can skip this injection gas. It doesn't mean anything. Okay, so from here, we can click input. We can leave them blank. Results. Later on, we will have results after we run the model. Input again. As you can see, we don't have production data. From the MBAL model also, we don't have production data. Compressibility, constraints, injection. Yeah, we can leave it as it is. Wells connected to well 1, well 2, well 3, and well 4. Okay. Schedule, we can leave it as it is. So we can click validate. Data is okay. Okay. Click check summary again. Okay, so far so good. Click OK. Okay, so now you can see the gas reservoir is ready. All right, and also I will connect well 1 with the well model 1 created in Prosper, and also for well 2, well 3, and well 4. All right, open the well 1. You can see the label is well 1. Name mask is included in system. You can type in any comment here. I will comment well 1. Okay, well type, I can change it to gas producer. Model VLP IPR intersection. Okay, use volumes for red model. And again, I will browse and connect this well one with the actual Prosper model that I have created. All right. Okay, so this is the model. Tank connections okay. IPR and VLP still invalid. We will create or we will generate the IPR and VLP later in the GAP software. No constraints, no controls, no downtime, no conning, no schedule. Check the input. Pressure drop control, none. In this control, IPR, yeah, we need to input some numbers in this IPR, but we can skip it for now. VLP, if you have a VLP file, you can connect it here. Conning, we can leave them blank. Constraints, downtime, tanks. Yeah, we connect the well with gas reservoir model. Schedule, we can leave it as it is. Results, later on, we will have the results written here after we run the model. Okay, so still we need to input the data here, especially in IPR and VLP. Okay, IPR and VLP, and in IPR we have IPR layer, more, and grid view. Okay, we can skip it for now. I will connect the rest of the 3 wells with the Prosper files first. Click OK. You can see well 1, and I will do that also for well 2, well 3, and well 4. Okay, well 2, go to summary, connect with my well, well to Eng-Man, open. Okay, later on the IPR and VLP, click OK. And also well 3, go to summary, browse, okay. Find the well 3 Eng-Man, open, valid, okay. Well 4, browse, and then well 4 Eng-Man, valid, okay. So far so good. I will check it first. It is actually gas producer. Okay. Double click. Gas producer. Okay. Gas producer number 4. Okay. All right. So almost ready for these 4 wells. Let's check if we open or double click this line. Okay, so basically, if we open this line, we will actually open the well. Double click. Okay. So as you can see, this is just an imaginary line, imaginary connection. So no real meaning here. And what if we open here? Yeah, nothing if we double click. It's just imaginary connection. But we can go inside this line because it's actually flow line. Okay, so double click. All right. Now let's check the summary. Okay, the summary, it's good. Okay, we can call it line 1, comments line 1. Okay, correlation, we can use petroleum experts 5, and others we can leave them as they are. Okay, environment okay, pipe data none, schedule none. Now we go to input. Okay, time since production started, assuming 100 days. And then for the overall heat transfer coefficient, 3. Oil heat capacity 0.53, gas heat capacity 0.51, water heat capacity 1. Okay, and then description. This is the main thing. Okay, this is the main thing. Open the drop-down menu, line pipe with length. I will first change the length to kilometers. Okay, so I will close. All changes will be lost. No. Yeah, okay. Yes. Make sure you save, or later. We can do that later. Units, oil field. Okay. Edit units. For length, we go to length, L. Length, we change it. Open the drop-down menu to kilometers, km. Okay, click OK. Go back to the pipeline 1. Segment type, it's line pipe. Oh, actually, we can change the unit here. Kilometer. 0.8048. TVD 0. Okay, so at 0 depth, inside the emitter, 4 inches with roughness 0.0006. Okay, so far so good. Enter elevation as no TVD. And then rate multiplier 1, maximum length step 10,000 feet. Flow type tubing flow. Correlation, this is also important. I select petroleum experts 5. Okay, gravity coefficient 1, friction coefficient 1. All right. Now we can check this one, TVD 0 here. And environment okay. Environment okay. And then for the description, already okay. Matching, we can leave it blank. Constraint also. Schedule also. Results later on will be populated here after we run the model. Click OK. First line ready. Now to the second flow line. Summary, we can call it line 2. Okay, line 2, correlation petroleum experts 5. Go to input, go to environment or description, or environment first. Okay, surrounding temperature 32, overall heat transfer coefficient 3, 0.5351. Okay, water heat capacity 1. All right, go to description. Now the line pipe also with length of 1.1096. Okay, and then the depth, the elevation of our flow line, still on the surface. Okay, at 0 depth. the same inside diameter, 4 inches. Roughness the same. Okay, everything the same. Tubing flow, gravity coefficient 1, friction coefficient 1 also. Petroleum expert 5. Lift the constraint, lift the schedule, validate, data is okay. Click OK, click OK. Line 2, done. And then at the same, we do the same thing. Line 3. Line 3. Petroleum expert 5. Input, environment, 32 degrees Fahrenheit. 3. Okay. And then the description, the main thing actually. Again, line pipe. By the way, we can have choke, coated, flexible, or fitting. In this case, we install line pipe with length of 0.5 kilometers, 0, 0, 4 inches. Okay. Use as usual, no constraint, no schedule. Okay. Let's make it quick. This should be line 4. Okay. Line 4. Petroleum expert 5. Input, environment, 32. It's 3. Description, line pipe, 0.5, 0, 0, 4 inches. Okay, click OK. Now this line. Okay, we call it summary. Pipe, pipe, petroleum expert 5. Okay. Input, environment, 32. This one is 3, overall heat transfer coefficient. Description, it's a line pipe, 0.3 kilometers, 0, 0 inside diameter. This one is bigger inside diameter. Yeah, that's why, yeah, because we connect the flow lines from several wells. Okay, so this pipe, this flow line will contain gas with higher rate, bigger volume. So that's why usually we use bigger size of pipe. Okay, we keep the roughness, everything okay, no constraint, no schedule, click OK. Lastly, for the pipeline between manifold B and separator joint, okay, pipe 2, petroleum experts, input, environment, 32, 3. Okay, this one, 0,4, not too long, actually. 12 inches. Okay. Click OK. All right. So far, so good. So now we can also set the separator. Open the separator. You can see first we have separator parameters. We assume water separated to be 100%, gas separated to be 100%. Okay. Constraints, this is the main thing. Okay. Maximum gas rate, 250. So we set our system we set our system in such a way that the maximum flow rate that we have, that we operate, is only 250 million standard cubic feet per day. Okay, so that's our target. Okay, we give this information to our model, and yeah, the model will calculate it for us how the system can achieve this number. The model will recommend the operation system, the operation mode to us. Okay, we just give them this target. Okay, all right, to make sure it is 250 million standard cubic feet per day. Okay, we click OK. All right, we are almost done, but don't forget, we still haven't completed the IPR in each well. Okay, so double click on well 1, go to the IPR. Okay, okay, so now we will input this model with numbers. Okay, you can follow me. Layer type gas, the IPR type CNN. Okay, so actually, although we created IPR model in Prosper, we can also do that in the GAP. So it's okay if we do that here, and we must do that here actually. By the way, if you have created IPR file from Prosper, you can also connect or take the file here by browsing it. Okay, but now I will just input numbers in this model. So let's say the C parameter, make sure the unit. Okay, this is 0. Okay, 0.008772. Okay, just to make it quite detailed, in reality we just use maybe 3 numbers after the comma. Okay, but I just want to make it very detailed for example sake. Okay, all right. Layer pressure, reservoir pressure 5,300 with layer temperature 166. We can leave it blank. And then the condensate gravity 67 with gas gravity 0.77. Condensate gas ratio 22.2. Water gas ratio 1. And check the grid view. You can see it's automatically populated. Mask included, layer type gas, CNN, layer pressure, use IPR pressure drop, no. Okay. And others like this one, WGR, water gas ratio, condensate gas ratio, oil gravity, gas gravity, okay. All right. And also for the grid view, okay, more prediction fractional flow model, click edit if you want to edit it here. But in our case, we open the drop-down menu and use from tank model. Okay. Grid view, okay. Now you can see the layer 1 is okay. This section is okay. We use this fractional model or relative permeability from the tank model, from the MBAL. And the grid view already also okay. Again, abandonment, leave it as it is. No constraint, no coning, downtime 0, tanks, schedule, now VLP. VLP, we can construct the VLP by using generate, or we can also import if we have created VLP files from Prosper. Okay, I have created 4 VLP files from the Prosper, but let's check if we generate the VLP instead. Okay, I use allow left-hand side intersection for optimizer. Okay, this is proper calculation. We allow left-hand side intersection. Let's do generate. Okay, generate for gap model. Okay, for gap model. All right, follow prosper file, the PVT method, generate. Let's wait. VLP generate finished, but some errors encountered during generation. Why? We need to be careful. Generate. Okay, that's why we need to prepare the second method, actually browsing the VLP files from the Prosper file. Okay, browse this one. Okay, VLP1, well1 VLP. Okay, this VLP file is generated from the Prosper. Okay, click open. Here, this one is better than generating it. By the way, let's generate if we can generate. Still error. So yeah, we will use this VLP. Okay, so far so good. Validate, data is okay. What is calculate? But we can skip it for now. This is actually if you have gas rate, WGR, condensate gas ratio, and manifold pressure. What will you get for other parameters? Maybe we can do that later. Okay, so now we can click OK. Well 1 is ready. Go to well 2. Go to IPR layer. Still, layer 1 is invalid. Okay. IPR type CNN 0.00319334 with N 0.995. Okay. And then the layer pressure 5,300, layer type 166, condensate gravity 67, gas gravity 0.77, condensate gas ratio 22.2, water gas ratio 1. Okay. Layer type, yeah, gas. Okay. More relative permeability from tank model, from MBAL. Grid view automatically populate with data we have provided in IPR layer section. Okay, IPR is okay. Now VLP, let's try generate again. Generate. Oh, still errors. That's okay. Click OK. Now we click browse. Tag well to VLP. Open. All right. Validate. Okay. Click OK. Well 2 is ready. We do that also for well 3. Go to IPR layer. Okay. CNN. C is 0.00932. This is 0.957. 5,300. 166. 67, 0.77, condensate ratio 0.2, WGR1, okay. And then more, use tank model, grid view already populated. VLP, let's try again. Data, if you have. Okay, if not, click OK, OK, or close. Generate, still errors. So again, we need to browse with and take the already prepared VLP file. Okay, click browse, take well3 VLP. Okay, validate. Okay, what if we check plot? Nothing here. Oh, wait a minute. Oh yeah, we can generate the VLP plot actually. Yeah, because we already have the VLP, right? TPD plot. So this is our VLP, pressure against the flow rate. Okay. The temperature. Okay. C factor, mixture velocity, erosional velocity, right? Maximum grain diameter. Interesting. Turner velocity. Okay. For liquid loading, right? Erosion flag, Turner flag, erosion rate, corrosion rate. Okay. Yeah. If you want to do calculation, yeah, you can calculate here. Let's say water gas ratio 10, just to check it. Water gas ratio 22.2, condensate gas ratio 0, manifold pressure 1000. What happened? Click calculate. Yeah, and the other will be calculated. So this is the flowing bottom hole pressure, will be calculated, flowing wellhead temperature, C factor, Turner velocity that is happening, Turner velocity. This is the critical velocity that is required in order to avoid liquid loading. That's the meaning of Turner velocity, this velocity. And others, Turner flag, erosion rate, corrosion rate, okay? So you can do the sensitivity, you can just try the flow rate, WGR, condensate gas ratio, or I think this should be 1, and condensate gas ratio is 22.2. Calculate, okay? All right, so far so good. And of course you can plot there, okay? And you can check the Turner flag, either you are safe or you are not, okay? Gas rate and Turner flag, or I mean Turner velocity, I should do instead. Turner velocity, this one. Yeah, okay. All right, so now you can close, click OK. Results, not yet. Click OK. And lastly, well full. Go to summary, input, IPR, IPR layer. Okay, don't forget well full. Okay, lastly, this is CNN 0.0562. This is 0.842, and then 67, 0.77, 22.2, water gas ratio of 1, more, the relative permeability from tank model, grid view, already populated? Oh, not yet. The layer pressure, 5,300 and 166. Everything changed to green colors. And again, lastly, the VLP, try generate, still not yet. Okay, still errors. Okay, so we will use the already prepared file. Click browse, choose well4, validate. Again, if you want to plot, all right. Okay, so we can close. Okay, so now we are actually ready to operate and to run the model. We can try once again, generate. Either we want to generate IPRs, but we already have that. Okay, let's check generate well VLPs. All, generate. Let's check it out. Yeah, still errors. So we will use the already prepared VLP files. Okay, so now check again the separator constraint. Okay, now we will run the prediction, or first let's check the solve network. Not run prediction. Okay, what is if we do main? Okay, not yet. This is at source. What do we have here? Summary, input, separator, constraint. Okay, this is to run prediction. If we do next, here we will set the separator pressure. Okay, and we will set the separator pressure, the system pressure at 1000. But before doing that, let's check this. Back. Yeah, you can see if we highlight the line, flow rate of oil still 0, stock tank barrel per day, water still 0, liquid still 0, also still 0, 0, 0, right? Still 0, still no flow. Okay, so by running the model, we actually flow the system. Okay, we start the system until it reaches steady state operation. Okay, so here we will do steady state simulation. So after we run the prediction, we run the model, we will have the flow rate here in flow line 1, 2, in pipe 2, line 3, line 4. Okay, that's the meaning of this system to run. Okay, so yeah, we have the gas reservoir, we have 4 gas wells, we have the flow lines, we have the manifolds, we have the pipeline, we have the separator pressure, which will govern the separator system or system pressure. Okay, and let's check the result. All right. Okay, go to prediction, run prediction, start date. Yeah, we can start from January 1st, 2008. Step size 1 month. End date, let's say 10 years. So it will end at 2018. No DCQ prediction. Next, still 0. Next, separator pressure or the system pressure is 1000. Next, so the mode, no optimization, rule-based, optimize with all constraints, optimize with potential constraints only, for the basic case, for the easiest and the simplest operation, we start with no optimization. So the system, the gap will only give us the separator pressure of 1000 psig and the maximum flow rate of 250 million standard cubic feet per day of gas. Okay, so calculate. You can see the gap will run the MBAL, the gap will run also the Prosper, and the calculation happens. You can see this is the error, numbers of iteration, the step. We are now in 2014, and the step maximum 122. Okay, so already done. It's quite fast. We can calculate, we can go to the main window, and we can also plot tanks or plot nodes. Let's plot tanks. What happened? Equipment type, tank, gas reservoir, plot, last prediction run, gas reservoir. Let's check the average gas production. Okay. So you can see this is what happened. Okay, you can also check the average oil production, the reservoir pressure. Okay, reduced from 5,300 down to 3,000 psig. Average gas production and others. Let's close it first. Main, still 0 stock tank barrel per day. Still not very good. I think it should change the results. Yeah, you can see we now have the results. Okay. And plot. So by operating the gap, we will have, yeah, flow rate or all conditions in each line, in each pipeline. So in gas rate, you can see pressure drop. You can know the pressure drop, right? It's very important. You can know the water rate. Interesting. Click OK. Yeah, usually we will have everything written here. So if we, yeah, touch this line, there should be flow rate of oil, something stock tank barrel per day, flow rate of gas also, and others. Or let's check the line first. This is for line 1. You can plot the gas rate. Okay, again, the pressure drop. You can plot many things. C factor, pressure drop due to friction, pressure drop due to gravity, pressure drop due to acceleration, right? It's important. But the most important thing is of course the gas flow rate. Okay, click OK. J3 also, results, plot, liquid rate, mass flow rate. Okay, click OK. And line 4, plot, gross heating value. Okay, pipe and pipe 2. Beautiful. Also the separator. This is the results for separator. plot gas rate. Okay. Yeah, you can see we still cannot reach, or we cannot keep maximum flow rate of 250. Here we achieve 300, although we said earlier that the maximum flow rate is only 250 that we will allow. So yeah, we can do the separator again, for example, change the input here, or we can do prediction, next, next, next. But now we will use either rule-based, we can try, or optimize with all constraints. Okay, calculate. So the gap will optimize the system with all the constraints that we give. Just want to check what will happen. Okay. So if you have many constraints, you can put all the constraint in the gap software and the gap will calculate it for us. So let's check the plot tanks, plot reservoir pressure, average gas rate, remove all. Yeah, still above 300. Still no difference. But regarding the results, I think we can, yeah, it's quite satisfactory, these results, the oil rate, the gas rate, water rate, and others, right? Yeah, so basically this is the network simulation. This is the integrated simulation covering the reservoir simulation using material balance with MBAL software, and well modeling, well simulation using Prosper software, and the integration, the network simulation using GAP software. Okay, so it's quite easy, but of course you need to take some time to set everything up, the MBAL model, the Prosper model, also the GAP model. Okay, so I think we can call it a day. Maybe in the next section, we can discuss about other cases. Okay, but hopefully you already understand the sequence, the big picture of the integrated simulation. Okay, integrated petroleum simulation from reservoir simulation, well simulation, and network simulation, or production systems simulation, or surface facility simulation. Okay. Okay, but lastly, maybe, what if we solve network? Is there any difference? Yeah, we can have several pressure scenarios, but here we use only one. Next, no optimization, calculate. Okay, very fast. Now, yeah, actually, you have that now. So actually, you can do prediction and you can also do solve network. Okay, what I've just done is actually solve the network. Okay, and now after solving the network, you can see the results in each pipeline. All right, you have that. You know the flow rate across the flow line 1. It is 100 or 1,823 stock tank barrel per day of oil. The water flow rate, the liquid flow rate, the gas flow rate, the pressure at this flow line, which is very important, and line 2 and line 3 line 4, and pipe 2 separator. Okay, so at this condition, you can get gas flow rate of 300 million standard cubic feet per day. Okay, and you can check the warning. Maximum gas rate separator constraint violated. 306 instead of 250 million standard cubic feet per day. Okay, so maybe you need to modify something so that you can reach the setting the maximum flow rate that you desire, which is 250 million standard cubic feet per day. Okay, so basically the current system, the current mode with separator pressure of 1000 cannot reach or cannot keep the flow rate at 250, but it can deliver more than that. It can deliver 306 million standard cubic feet per day. Okay, so I hope that's clear. So we can call it a day, or maybe lastly, if we plot gas rate, yeah, this is results plot for separator, or yeah, click OK. Results, detailed, all items. Okay, this is for separator pressure of 1000 actually. Okay, so basically with sulfur, you can do like this one. You can do 500, 800, 1000, 1200. And next, calculate. Main. Okay. Bottleneck. Yeah, you can see we have bottleneck in this flow line, maybe because it's too small, only 4 inches, but we can plot the results, detailed, all items. You can see like this one. So for example, for separator pressure of 500, we can get gas rate this much, 800 this much, 1000 this much, and 1200 this much. You can plot, you can see. So for gas flow rate and oil flow rate, if we increase the system pressure, of course, we will get lower flow rate, gas rate or oil rate. Okay. But as I said before, if you want to optimize the production, usually you can do that by lowering the separator pressure or lowering the system pressure. But of course, if you lower the separator pressure, later on maybe you will also have another problem, like the compressor power that is required to increase the pressure, okay, from the output of the separator to the cellus system. Okay, but that's discussion for another day. But by doing the solve network, we actually do the sensitivity analysis. So solve network is actually sensitivity analysis, but the prediction is actually forecasting. Okay, so you can do either prediction or solve network or sensitivity analysis. Okay, so I hope that's clear. We already cover MBAL model, Prosper model, and GAP model. All right, so that's all. See you again in the next lecture. All right.